Hello, everyone. Welcome back. We are in the second half of Chapter 8 in Fundamentals of Inorganic Glasses. Last time we dealt with elasticity of glass, and today we are going to finish the chapter with hardness of glass in Lecture 17. Hardness. Hardness is another property characteristics of solids, just like the property of elasticity. Hardness is a property that separates the solid phases of matter from liquid. Hardness is a more complicated property than just elastic moduli. Hardness is related to the material's elastic response followed by its plastic response to an applied stress. The elastic part of the response is reversible. That's part of the definition of elastic, which means that once the stress is removed from a material, any of the elastic strain is recovered, which means that the original dimensions of the material would be recovered after removal of that stress. However, if the magnitude of the stress is increased, the stress can become high enough to produce irreversible, also known as plastic deformations of the material. By irreversible, this means that the plastic part of the response is not recovered after removal of the stress. Where this transition occurs, once you go beyond this elastic limit, this is called the yield point or the yield strength of the material, and this represents the end of the elastic region on the stress strain curve. Hardness is a measure of the resistance of a material to being penetrated or eroded by another material's sharp projection. So it is a kind of complicated response of the material that has contributions from both the elastic part as well as the plastic part. Now, the typical way of measuring hardness is through indentation. There are different types of indenter geometries. For most glasses, the hardness is typically measured with either a Vickers or a Knoop diamond indenter. Both are pyramidal in shape. The difference is that the Vickers indenter is a square pyramid, as shown here. So the diagonals have the same dimensions in both ways, labeled D, and the angle of the indenter is 136 degrees for Vickers. Alternatively, the Knoop indenter is pyramidal, but it is elongated along one of the diagonals. So one of the diagonals is longer compared to the other, and the ratio of the diagonals follows the long diagonal divided by the short one is equal to 7.11, and the ratio between the short diagonal and this thickness here, T, is 4.28. So following that geometry, that would give you the Knoop indenter. Hardness is calculated based on either a Vickers hardness number, VHN, or a Knoop hardness number. Either way, the hardness is a measure of force over area. For the Vickers hardness, this is 2 times the force times the sine of theta over 2, where that theta is the Vickers angle of 136 degrees, divided by the diagonal of the indent that is left, d squared. And so when we put in the particular angle for the Vickers indenter, we get out in front here that is 1.854 times our load, F, divided by the diagonal squared of the indent. So a higher hardness would mean that the material is able to withstand a higher load with a smaller amount of the permanent indentation in the material. Likewise, for the Knoop hardness number, we've got a different geometry, and so there's a different prefactor out in front, but the Knoop hardness number is calculated as 14.23 times the applied load here, F, divided by the long diagonal squared. So this prefactor here of 14.23 accounts for using the long diagonal in the denominator rather than the short diagonal. Either way, you get values of hardness, but please note that the value of hardness that is quoted is not just a function of the material being measured, it's also a function of the way that it is measured in the geometry of the indenter. So always make sure when you are looking at hardness data or reporting hardness data that you give all of the full details about how the hardness measurement was conducted and what geometry was being used. Another type of geometry that is used, although not quite as often, is the Brinell or spherical indenter. This actually shows a result of optical profilatometry using basically a laser scan across the surface after the indentation. And you can see this spherical indent that remains in the surface of the glass. Using this type of laser profilometry, you can get a nice measurement of the imprint of the indentation that is left in the surface of the glass and calculate things like the volume of the indent, the depth of the indent, the volume of the material that is piled up around the perimeter or the circumference here of the indent. So all of those things are possible using laser profilometry. Now, when an indenter comes down into and penetrates into the surface of the glass, different types of deformation modes are possible. One of the things that you'll see here is that under this permanent indentation, there is some region where there is likely to have densified glass, permanently densified glass under the original indentation. At the same time, some of the material is going to flow out of the way through shear flow, and that's what creates these mounds around the circumference or around the perimeter of the indent. And one of the things that we want to know when measuring hardness is not just what the hardness is, but what are the relative contributions of the different types of plastic deformation. In other words, how much of the volume that has been displaced here goes into forming these mounds around the perimeter versus becoming permanently compressed underneath the indenter. And if we take one particular cross-section across that Brinell indentation, we can get a trace from the profilometer. And this shows the height here in microns, where the dashed line is the original surface of the glass. And anything that is above that would be the mound around the outside of the indent. So this is material that is piled up above the original surface. And anything that is below here, this is the result of the permanent indent that is left in the glass. Now, we tend to classify glasses as either normal or anomalous based on their response to an indentation. A normal glass shows more pileup on the outside. So a normal glass like soda lime silicate, for example, is a normal glass. Most of the modified silicate glasses are normal glasses where they've got a substantial amount of non-bridging oxygens in the glass structure. This leads to a breaking of the connectivity of the glass structure, which allows for easier flow. And so with these normal glasses, they are able to flow more readily to actually move some of the material, transport some of the material from this volume of the indentation to the outside perimeter here where there is pileup. So normal glasses will tend to show more pileup. Anomalous glasses, which is typically fused silica or glasses that are very high in silica, these have basically topologies that are more fully connected. And so it is more difficult for like a fully connected silica structure to be able to flow. And something like silica has a rather open network at the same time, which means that there's more opportunity for compression. So because of this combination of a more open network, together with having a fully rigid network, glasses like silica or glasses very high in silica will tend to show more densification and less shear flow, so less pileup. And because these glasses are less common compared to the modified silicate glasses, these are called anomalous glasses. The reality, of course, is that there's always a mixture of these two responses, but anomalous glasses tend to prefer the densification mechanism, and normal glasses tend to prefer the pileup mechanism. Now, if we look at this schematic diagram, this shows the many types of mechanical responses that a glass can have in response to an indenter that penetrates into the surface of the glass. So if you have the glass surface here shown by this purple dashed line, and an indenter is penetrating into the glass surface, there's different types of responses that will be observed. The one that is labeled here in the light green is elastic, or this is the deformation zone. So this contains all the material that has some level of deformation in it. Within that, the outermost part tends to be the elastic deformation piece. These arrows here around elastic deformation indicate the amount of the material that, or the amount of strain that is recovered after removal of the indenter. So if the indenter comes down, there is some combination of elastic and plastic responses, but when the indenter is retracted, some part of that deformation is recovered. That part that is recovered is the elastic part of the deformation. So even though, we've gone beyond the yield point here with this indentation, some part of the mechanical response is elastic, and that part will be recovered. Some part of the plastic deformation will be permanent densification. Because it is permanent, that means that it is plastic or irrecoverable. And so after the indenter is retracted, after it's drawn back up again, that densification is permanent. And then part of the plastic deformation will be plastic flow or shear flow. This is where some of the material just flows out of the way. So it gets removed from this region of the indenter and it goes into this pileup regime around the circumference of the indenter. So these are two types of plastic deformation that occur, plus the elastic deformation. One other type of irrecoverable deformation that can occur is the formation of a crack. Cracks will typically pop in the region where you've got maximum tensile stress, which is actually a little bit below the tip of the indenter. There'll be a pop in of a crack, kind of nucleation of the crack followed by a pop in of the crack. So the crack will nucleate underneath the low point of the indentation, and then it can pop in and have the crack propagate all the way to the surface. And what you see if you look at kind of the downward view of the indenter after the cracks popping in, if it's a Vickers indenter, it would be a square pyramid shape as shown here, and then you can have cracks popping in off of each of the corners of the indent. And measuring those crack distances can give you the fracture toughness of the glass, at least based on an indentation measurement. And we'll get to that a bit later when we deal with fracture toughness. For now, I just want to point out that if you are doing a hardness measurement and cracks have popped in, that means you used too much force. And the resulting hardness value that you get is going to be inaccurate because a lot of the applied energy that you put into the indenter has been released by creating these new surfaces of the cracks. And once we get to that point, this is not how we want to see the energy dissipated to do an accurate hardness measurement. So that data should not be used for reporting hardness. You should use a load on the indenter that will be large enough to get a permanent plastic indentation left in the surface of the glass, but not so high that you're popping in cracks. And that's where you want to be in order to get accurate hardness measurements. Now, what I was just describing was based on loading the indenter, unloading the indenter, and then after unloading, you look at the area of the um, indent to see what is the size of the impression that is left. Another way to conduct hardness measurements is called dynamic hardness measurements. With dynamic hardness measurements, you're actually measuring the load as a function of penetration depth, and you get the entire loading curve So starting with zero load and zero penetration, as you increase the load, the penetration increases until it gets to a max. The maximum depth of penetration here is this H max. And then upon unloading, the unloading curve doesn't retrace the initial loading curve because we have some plasticity as part of this response. And the unloading curve is coming back down. And when you've got complete unloading, so now a load of zero, there is some final depth of the indent that remains, and that is this little h sub f. Normally, this is the only thing that we would see after a normal hardness measurement is, how much depth is left or what is the area or the diagonal measurements of the impression. But with a dynamic hardness measurement, you get these entire curves. You get the entire loading curve and the unloading curve, which gives you additional information about the fraction of elastic versus plastic responses. And you can quote then two dynamic hardness values. One of them is based on the H max. So this would be just based on loading without even accounting for unloading. How deep is the indenter penetrating into the surface of the glass? That gives you this HVL dynamic hardness value. And then the other one is after the indenter is fully retracted based on the size of the impression that is left. If we look at some loading and unloading curves for some common silicate glasses under dynamic hardness measurements, if you look at just pure silica here, pure silica is coming up with these diamonds, and this has the steepest slope here. This is because of the greatest rigidity, the greatest connectivity of the glass network. And when that is unloaded, it, most of it is recovered. I mean, the greatest part of the response here is elastic, and the plastic part we know is, of course, primarily densification under the indenter. Now, if you go from vitreous silica to a modified silicate glass like soda lime glass, that is the open squares shown here. The slope is a little bit less, and the amount of recovery here, you see the unloading curve comes down, and actually the contact area that is left is about the same, but the mechanism of the deformation is a little bit different because of its normal response, meaning that you'll have more shear flow in soda lime. But a more extreme case here is lead silicate. This is quite a bit softer, and what you'll see is that after unloading, that the area that is left is quite a bit larger in lead silicates. Now, what is it that is controlling the hardness of glass? This can all point back to the connectivity of the glass network, going back to Phillips's constraint theory and counting the number of rigid constraints versus the number of degrees of freedom in the glass network. What we can see on the left-hand plot is for this series of glasses, these were a series of borate glasses, that the measured values of hardness here under two different loads, if we plot them versus the number of rigid constraints per atom, this would be the number of rigid constraints per atom at the temperature where the hardness is measured. So this is a room temperature measurement, that there's a linear relationship between the measured hardness and the number of constraints per atom. And so this is giving us this linear relationship, which lends itself to this formula shown here at the bottom, where the Vickers hardness is equal to some constant of proportionality times the number of constraints per atom minus some critical number of constraints per atom where that hardness goes to zero. You can see in this left-hand plot that that is occurring for this series of glasses with 2.5 constraints per atom. So basically any constraints that go beyond this 2.5 number are contributing to the rigidity in the third dimension for this particular set of glasses. And that is what is providing the resistance of the indenter. And that is what is increasing hardness. So the greater the number of atomic constraints, the higher the hardness. If we take the same data and plot it versus a compositional variable instead of versus the number of atomic constraints, you can see that there's excellent agreement in this case. These are borate glasses, and the reason for this maximum here is that this maximum corresponds to a maximum in the number of fourfold coordinated boron, as you go beyond that, then you start to form non-bridging oxygen. So it's just another example of the boron anomaly in action. What happens if you replace some of the anions in the glass? So if you take out some of the oxygen and replace it with nitrogen, the number of constraints here per bridging oxygen would be one radio constraint per bridging oxygen because there are two bonds, each shared by two atoms. So 2 divided by 2 is one radio constraint per oxygen. And then there's one angular constraint per oxygen. So this is 2 constraints per oxygen. If you have nitrogen, nitrogen has 3 bonds, each shared by 2 atoms. So it's 3 halves radio constraints plus 3 angular constraints. So that gives us 3 plus 1.5 or 4.5 rigid constraints per nitrogen versus 2 rigid constraints per oxygen. And as a result, as oxygen is replaced by an equivalent amount of nitrogen, you can see that the hardness of the glasses increases rather dramatically. The dashed curve here shows the prediction of how much the hardness would increase just based on a counting of the number of constraints. And then the points here are the measured data. And there's very good agreement, of course, between the theory and the experiment. And we also note that with 20% equivalent replacement of nitrogen for oxygen, the hardness is increased by about 20%. So it is a rather substantial increase in hardness based on nitriding the glass. So to summarize, hardness is a property of solid materials that quantifies the resistance to permanent deformation from sharp contact. Vickers and Knoop indenters are the most commonly used geometries. Hardness is linearly proportional to the number of rigid atomic constraints in excess of 2.5 rigid constraints per atom. All right, that is a wrap on chapter 8 for elastic properties of glass and hardness of glass. Next time we move on to chapter 9, which covers viscosity. And I believe we've got 3 lectures on viscosity. We're going to cover the viscosity in general, viscosity measurement techniques, models of liquid viscosity, as well as the composition dependence of viscosity. All right, thanks everyone for watching. I will see you next time.